In this video, we're going to be talking about ellipses. An ellipse is a set of all points in the plane, the sum of whose distances from two fixed points, which are the foci, is a constant. Foci basically means the plural of focus. So we basically have two focus here, and we call that a foci. What does this mean? If you look at this diagram, if we have two foci and we add their distances to a particular point, and perhaps like if we look at another point here and we add these distances, this is always going to be a constant. So the sum of the lengths of the purple line, sum of the lengths of the orange line and the red line are always constant, and that's how an ellipse is defined. Let's say in this diagram we have two foci, one positioned here, and I'm going to be denoting that by f prime, and its position is at negative c comma 0, and here's another foci around this point, which is f, which is c comma 0. So this is like it's c units in front here and c units behind here. If we looked at the distance of this from a particular point, let's say here, and we define it to be this point as P, which has the coordinates x comma y, we can derive the standard equation of an ellipse. So let's say that this constant, let's assume this to have the value 2a, a is just a constant, and we can calculate the magnitude of Pf prime plus Pf, which should be equal to twice of a, the constant. Using the graph, you can calculate the distance between these 2 points and the distance between these 2 points, so which will turn out to be x plus c squared plus y squared plus x minus c squared plus y squared is equal to twice of a. If we go ahead and rearrange this equation to this form, if we have x minus c squared plus y squared is equal to twice of a minus x plus c squared plus y squared, and then we square both sides. I'm going to leave the details of this to you, but if we square both sides, we have something of this form: c squared plus y squared is equal to 4a squared minus 4a square root of x plus c squared plus y squared plus x squared plus 2cx plus c squared plus y squared. You can work this out. You just have to square both sides and expand. So basically like squaring each of these sides, okay? And square both sides. Okay. If you simplify this, you would come across something like this. If you continue to simplify that and cancel out terms, you will come across this: a squared plus cx. And now since there's a square root, we would simplify again. So we simplify by again squaring both sides, and so you would be getting something like this: a squared multiplied by x squared plus 2cx plus c squared plus y squared is equal to a to the power 4 plus 2a squared cx plus c squared x squared. I'm going to again leave the details to you to solve through. And finally, if you rearrange this equation, you will come across this. A squared minus c squared. So A and C here are both just constants. These are, so A was a constant we defined. It's just a summation of their distances. And C is just a point, so it's also a constant. So if we redefine that, A minus C squared, if we define that to be a value, another constant, which is B squared, we would just have this equation. Sorry. So we come across this, and finally, if you divide both sides by this quantity, a squared, b squared. So if you divide all the terms by a squared, b squared, you would be left with x squared over a squared plus y squared over b squared is equal to 1. And this is our standard form of the ellipse, which is centered at the origin, right? So standard form. So we can have shifted ellipses again. We can also have here something to note though here is A is greater than B, and we might have an ellipse that is longer stretched out on the y-axis instead if we have a different orientation. So we'll look at that next. Let's now look at an interpretation of A and B here. So this distance is a C, right? This length here is actually A. This length here is also A. So the distance, the maximum distance on the y on either side is each the B. So what we would say is A is the length of the semi-major axis. So the one that is longer is called the major axis. So this whole thing, this twice A distance, is the distance of the major axis. Okay, and this distance is for the minor axis. So as you can definitely see, the minor axis is always smaller than the major axis. And so if we had an equation of this form, like y squared over a squared plus x squared over b squared, where we always assume that a is greater than b, right? A is the length of the semi-major axis, and this is the length of the semi-minor axis. Then we would have a shape like this. We would have a vertically stretched one. Now before we go ahead and discuss about all of the parts of ellipse, I've drawn out a clearer picture here, but we are going to define a quantity, and this quantity is called the eccentricity. Eccentricity is just a measure of, it is something that characterizes the shape of a conic. And it is just a constant. It's again just a rearrangement of A, B's, and C's, these constants. And what it basically tells us is how circular or uncircular the shape of a conic is. So let's see how we can define this quantity. The eccentricity is again just a constant. This is a ratio of the C over the A. Now what is C? C, if you remember, was the distance from the center to one of the foci, right? So f prime had negative C comma 0, and this is just the origin, so I'll use O, I guess. And this one was C comma 0, right? So the ratio of the distance from this origin to the focus divided by the distance of O to one of the vertices. So you can see that this distance is definitely going to be less than 1, right? It always should have a value of less than 1 for an ellipse here. So an ellipse has an eccentricity of greater than 0 but less than 1. Let's have a look at a quick view of how this works. So if the eccentricity is very small, you can see that the graph is much more circular, right? So it deviates from being circular when the eccentricity is larger. For example, if the eccentricity is more than 1 or like 1, you see there's a parabola, right? And if it's too large, you can see it's forming like a hyperbola. And so this is just a constant that determines that. So what is C here? If you remember from what we did a while back, we defined a squared minus c squared equals b squared, right? A squared minus c squared is equal to b squared. These are just constants again. And so c squared was equal to a squared minus b squared. So a squared minus b squared. And so the eccentricity is like a square root of a squared minus b squared over a. We can write this in a simpler form, of course. We can define this as 1 minus b squared over a squared. So this is eccentricity. And what we're going to do is we're going to talk about parts of this ellipse using this quantity. Now, for example, the focus, or like the foci, are at plus minus c, as you can see here. We can also write that as plus minus ae. And that is, well, you can prefer to use the c, but ae, or like in terms of eccentricity, we will be able to describe some other parts as well, so that will be useful. So let's go ahead and look at all the parts of this ellipse. So the center, which I have used O here, is at 0, 0. Again, you can have a shifted ellipse, which will have hk, and so the equation would be different a bit by that. The foci are at plus minus ae, comma 0, right? It's not shifted on the y. So, or you could also write plus minus c, comma 0. And this represents our points f prime and f. What other points do we have? We have the vertices. Now, this is just a plural of vertex because we have 2 points, 2 extreme points here. These are called the vertices. So vertices here are a and a prime. I'll label that right here. So this is at plus minus a, comma 0. And this is a and a prime. There are also co-vertices because these are also extreme points. They are turning points. So these are called co-vertices. Co-vertices. And these have the value 0, comma plus minus b because they're on like a shift on the y. We also have the equation of the axis. So equation of minor axis. Let's start with the major axis. This is the longer axis. Equation of major axis here is y equals 0, and that is representing my point here, a and a prime, right? It's representing a and a prime. Sorry, it's representing the line a prime, this whole line from a to a prime. And then we have the equation of the minor axis, equation of minor axis, which is here x is equal to 0, and this is representing bb prime, right? The line here, bb prime. So bb prime. So how do we define the length of each of these axes? The length of major axis is represented by, well, it's quite clear here that it's just 2a, and this is again just the length aa prime, right? The length of the minor axis is just 2b. and this is again just this distance from B to B prime. So if we drew an axis at A prime, the whole line is the equation of the major axis. The line here would be the equation of the minor axis, something like this here, right? And the lengths are 2A on the major axis and 2B on the length of the minor axis. Now in this diagram, the directrices are D and D prime. So we have two of the directrix as compared to the parabola where we had one. And we can see that it's just a bit shifted from the vertices. So how we can define the equation of the directrices, equation of directrices are x is equal to plus minus a over e. So that's again the eccentricity. So if we kind of label this diagram to have, so this whole line, let's say this is z and this is z prime. So the equation that goes through d and z prime and d and z, these are the directress. Now for the equation of the latest rectum, if you remember, the latest rectum was just a point that went through the foci, right? Just went through the foci and went up to cutting a part of the conic. So this would be x is equal to plus minus AE. And AE, if you remember here, is just the foci, right? So whenever we have a line passing through the foci somehow, here and here, that gives us the equation of the latest rectum. And the length of this latest rectum, is 2b squared over a. So this is just a use of constants, 2b squared over a. So if we drew a latest rectum here, yes, so let's draw one here. The length of this is 2b squared over a. Similarly, the length of this is the same, right? So this is also 2b squared over a. Now something to note here is we have brought all of these definitions in from an ellipse that's of this shape. But if we did have an ellipse of this type of shape, I hope you can interpret this just as we did for a parabola. The foci would be along the y, so it would shift into this form. The a is now here, right? This is 2a. This is the major axis, and this would be the minor axis. So the vertices would be at 0, plus minus a, right? So all of these interpretations would have to be changed. You would have to flip the sides and find out each points. You can draw a graph if that helps. Otherwise, you can simply interpret it that way. That's it for this video. In the next video, we'll look at some examples of ellipses.